another statistical topic. But before I get started today, I want to notify you that I've already uploaded Meet and One makeup. So like I said, the makeup will be left open for some hours, some days, except that you can only spend 60 minutes, okay, on it. So the moment you start, your time is going to be running out. I think I only asked just 2 questions. So, I believe you should be able to finish that. So, like I said, in that makeup, you got nothing to lose. Okay. It's just an opportunity to improve on grade. Okay. So, once again, I want to welcome you to my lecture today. Uh, the title is a power transformation. Of course, we started transformation on Monday. The idea of transformation is actually to fix a problem, which means one of the assumptions have been violated and we needed to fix that. Okay, so in the outline, I'm going to have a review of previous chapters, then transformations of linear regression. Now, let me start with reviewing on previous chapters. There are 4 main process, or let me just say 4 steps. We got 4 steps when we basically want to investigate relationship, okay, among variables. The very first step, 1, you specify your model. Okay, you specify your model. Those of you online, can you confirm if you can see what I'm writing on the board? Those of you online, can you confirm that? Like, can you see what I'm writing on the board? Like, okay, can you see this guy now? Specify your model. Can you confirm if you can see that? Those of you online.
You have to write a little lower.
Oh, a little bit lower, right? You need it to be up, right? Like, okay, let me see. I'm gonna see the setting now. So to see whether that work, because I want to make sure you really see what I'm writing. Okay, so you said I should like go a little bit lower. Do you see this guy now? Do you see that? Those of you online? Can you confirm if you can see that? Those of you online.
Still a little too up there.
Oh, see a little bit up. Okay, so like what about this guy now?
That's good.
That's good. Thank you so much for confirming that. So when I talk about 4-step process, 4-step process in modeling in general, in modeling in general, okay, we actually we're going to go through 4-step process. Number 1, we specify your model. Number 2, okay, now when you specify your model, the next thing we're basically going to do is model estimation. We estimate parameters in the model. The next process is evaluate your model. Evaluate your model. When you are evaluating your model, how valid is your model? You are testing assumptions. Does that make sense? You are testing assumptions. And the last one, when everything is nice, then you make inference. Okay, you make inference. Okay, but what if in a situation where we are validating, okay, you are evaluating your model and there's a violation of assumption, then we need to fix the problem. And that is what lead us to what we want to do now. We basically want to fix the problem. Okay, and that is what we call transformation. Now, transforming, the reason why there's a violation in the first place is because some variables are not in good statistical standing. And that is why if we want to transform a model, we are actually transforming variable in the model. And that's why I call variable transformation. Okay, now, initially, we have different kinds of transformation. It's just like whenever there's a problem in real life, there are different options that one can use. Number one, like in transformation now, is linear transformation. Let's say W is the one that has a problem. By linear transformation, I can multiply W by constants. I can add constant to that. I can, when I'm doing this, that's a linear transformation. At times, it may not work. Okay, another transformation is going, okay, go ahead. Yeah, that's a very good question. At times, we do this a lot. Let's say you have your variable now in thousands. Maybe you have, but what you see that they wrote in the column, maybe they wrote 20, 25 under X, but they told you that is in thousand. It's more or less like multiplying this by 1,000. Even though, just like what you said, there will not be any effect. Does that make sense? And that is why linear transformation is not going to be the one we're going to consider. And that is the reason why this topic is called power transformation. Because we're basically going to focus on a transformation other than linear. Now, in a power transformation, I can take the square of W, which may be quadratic. I can do raised to power 3. Maybe I'm looking at a cubic. It can be a square root. It can be whatever. So another one is we have other transformation, where we're going to consider the trig, sine W, or we even consider situation where we got 2 explanatory variables. We could do the ratio of the 2. Okay. Now, I want you to see now something beautiful. I'm going to generalize this power transformation now. I got a W. The W is having an issue. And I want to transform that. Okay. I'm basically, the idea of the power is that I'm going to raise W to something. So what am I raising the W to? I'm raising W to lambda. If that lambda is not equal to 0, then I'm going to use that. But if lambda equal to 0, then I'm doing a log transformation. Hello? Did you get that? We're talking about log transformation the other time. It means the power is 0 when you are using the log transformation. Log transformation. Okay, now let's see how it works. Oh my God. I got a lot of something here. Now take a look at the first one. Let me first start. When lambda equal to 1, if W is raised to power lambda and lambda equal to 1, that's a straight line, right? There's no problem. Okay? The moment you have a straight line and you are using a linear function, there is no problem. You don't even need to transform anything. But what if in a situation where lambda equal to 2, then your data, you're going to have a curve like that. What if your lambda equal to -1? How when you, the the preliminary stage of every statistical investigation, particularly when you are looking at the relationship between variables, is to generate a scatter plot. So what I'm trying to tell you now, when I generate a scatter plot, okay, this is basically, I'm likely going to have different kind of shapes. Okay, what that is for that. When it is 0.5, you're going to have that. 0.5 is indicating a square root transformation. Okay, square root transformation. Okay, lambda equal to 0, the green line now, that is a logarithmic transformation. So before you can think of, taking a logarithm of a variable, maybe you've seen something like that. Maybe you see a curve that look like that. Okay, and that was why use log transformation for lambda equal to 0, because we've already seen that the log transformation always resolve to that. Now, what are the values that I considered here? I consider from -1 to 2. I mean, in this. So that's what I consider now. Now, why are we transforming the variables? Oh my God, why are we transforming the variable? Is more or less like, why do you come to my clinic? If I happen to be a doctor, okay, what is patient looking for in my hospital? Because the patient want me to solve a problem. There's a problem. Does that make sense? And if there's a problem, I, as a doctor, that I need to be able to do medical diagnosis, to be able to know the right medication. That's what we do in statistics as well, where we exploring our data is to be able to get ourselves familiar with the data. We want to know everything about the data. We want to know what is wrong with the data for us to be able to know what to do. So while transforming the variables, number one, just because a variable is given in the data set doesn't mean it is appropriate. We got some variables that are wrongly specified. Okay? And I'm going to give you an example now from economy. The study of a country economic development on child mortality rates. Okay, the possible variables would be child mortality rate, GDP, population. Now the question now is, I cannot just look at child mortality rate on GDP. That is not going to make sense. I have to define my GDP. I have to redefine my GDP. Now I'm talking about GDP per capita, or when you see your GDP per the population. Now, what do you think I'm doing here? GDP over population. I'm actually doing this guy. I'm going to walk you back now to be able to see. Oh my God, W1 over W2. Do you see order transformation? That's exactly what I'm doing. So it's more or less like I basically want to put my data, my variable, in an appropriate form. Okay. Another reason why we do transformation is to fix a problem. Okay, fixing a problem, the question is, does linear transformation help? If it doesn't help, then we can go to other form of transformation. Because of that, I'm going to walk you through an example now, where we actually want to model the salary of years of experience for professional workers. Now, what if we do a linear transformation on experience? Now, let me tell you this. You asked the other time that whether linear transformation work, right? At times, the idea behind linear transformation is maybe probably to put the data or the variable in an appropriate form. And I'm going to demonstrate to you now. Instead of me to be looking at the effect of experience on salary, do you know I can redefine experience in terms of work history index? The work history index is going to be experience minus 1 divided by 40. Maybe I'm using 40 hours a week. Instead of me to use just experience as an explanatory variable, experience may not be in a good statistical standing, but work history index is in good statistical standing. But if somebody now want to argue with me that I've already altered the situation, then I'm going to say no. And I want to prove now. When I plot salary against experience, I got that. When I plot salary against the work history index, the relationship is still the same. You can now see now I've not altered any arrangements, except that it will make economic sense to make my interpretation in terms of work history index, than using just experience. Okay, so that is what I mean. I want to go into another example now. I basically want to predict the brain weight from a body weight of mammals. Given the body weight of mammals, can I predict the brain weight? And I want to consider elephants now. Oh, elephants are found in Africa, in Asia, and so on like that. And, I plotted, I thought for generate this kind of plots where I plotted the brain weight against the body weight. But I can see two elephants that look like an outlier. African elephants and Asian elephants, maybe they look more heavier, compared to the other elephants. And if you have an outlier in the data set, it could be damaging, right? Okay. Now, some we may want to argue that okay, maybe we should remove them. We cannot remove them because they are genuine animals. We can't discard them from data. Otherwise, our conclusion will not be general. And we want our conclusion to be general, right? Now, if you ignore the violation and you go ahead and fit a linear regression model, you're basically going to have this guy. Okay, now, does this model fit the data well? Then I'm going to say no. There's possibility it doesn't fit the data well because I know the implication of the presence of outlying observation. Okay, now, some will suggest let's remove the two elephants. Okay, but I'm going to do something now. Let's try to remove the two elephants and let's see what is going to happen. Okay, removing the two elephants does not really solve the problem at times. It may not solve the problem at times. But why can't we look for a way to transform the variable, leaving the elephants, right? And how do we know that there's a violation? That was what we did last week. We can actually generate a diagnostic plot, like residual plots and the normal QQ plot. Now, if you take a look at the first one, the residual plot is having a pattern. Oh my God, the normal QQ plot is not even showing a diagonal line, which indicates there's a violations when you use a linear model for this. Okay, we now want to consider power transformation, but there is a lot of them. We're going to be thinking, should we do the reciprocal? Okay, now what we want to transform now is transforming both variables, right? Why both variables? The two of them are weight, brain weight from, and because they are weights, I can use the same level of transformation. And that is why if you take a look at the first one, I'm doing the reciprocal, right, of the two. I look at the log. I look at the cubic. I also look at the other one, but which one work? As you can see, oh my God, it's looking like a log, because the log and log is giving us a straight line. Take a look at that. Look at that. Okay, so the log actually work out. But let me tell you something. Why am I considering one a reciprocal, square rules, log? I want to compress the data. Why? Maybe positive skewness because of the two elephants. The skewness is going to be to the right. I want to bring it to the center. What am I going to do? If something is to the right and I want to bring it to the center, I'm going to compress. My transformation will involve taking a square, when you take a square root of a number, it's going to go down, right? Take a log. That is why you see this effort. Okay. Now, take a look at that. Okay, which transformation will you choose? Of course, I think I've already said that. Now, how do you know your transformation effort has worked? We look at the scatter plot. It's now a straight line. Then we're going to conduct a diagnostic testing. We're going to look at the residual before transformation. We look at the residual after transformation. Oh my God. The residual before transformation has a pattern. When it has a pattern, there's a violation of linearity. In fact, there's a violation of constant variance too. Okay. Then look at the residual after transformation. There's no pattern. That makes sense. We're not going to look at only residual plot. We're also going to look at the normal QQ plots. And you may want to know, this is what we did the other time. How do I generate the residual? Plot model 1. You remember? We did the other time. Plot, comma, model 1. Okay. What about the normal QQ plot? That will be plot model 2. Look at before. Oh my God. Look at after. It means the log transformation has really worked. We got a way in statistics to evaluate our intervention. Okay, to prove to the world that our intervention has worked. Okay, so why does log transformation work for this study? I'm actually, I think I got a kind of a message coming in. Okay. I'm so sorry. I'm going to stop the lecture now. I got a little emergency. So I'm going to continue on Friday. Okay. That's a little emergency. So we're going to continue from we need to generate, a QQ plot to investigate normality assumption. Of course, if you take a look at this guy now, okay, this is when I did not transform the two variables, and I basically use linear model. And of course, as you can see here, of course, we can see that assumption of normality is violated going by this. And of course, after transforming that, okay, where I actually take a logarithmic transformation of the two variables and I generate my normal QQ plot. Okay, you can see now. So this is basically looking good. Okay, so take a look at that. Okay, so we've actually investigated whether residual whether linearity assumption hold. Okay, and we've also investigated for normal assumption. So I'm going to go back again. Okay, this is having give me 1 second, let me see. Okay, I actually started by generating the scatter plots of the original variables, and you can see evaluations of, like you can see Asian elephant and African elephants. Okay, they are actually far from the rest. Take a look at that. So removing that, of course, that doesn't look as if we've addressed the problem in a way. And of course, we look at the residual plot and the normal QQ plots of the original, model where we did not transform. And as you can see, the residual is a violation. Looking at the residual plot, the residual plot actually have a pattern. And of course, there's a violation of constant variance as well. And if you take a look at the normal QQ plot now, okay, this is not even a diagonal straight line, so which actually indicate violations of normality. And we now want to try, like I said, we try different transformational efforts. And as you can see, based on what I've explained before, the log actually work. We log the response variable, we log the explanatory variable, and as you can see, that's actually giving us a straight line going by the the scatter plot that I generate. Okay, so if I also want to look at the residual plots, I mean the diagnostic plots, residual plots, and well, I mean the normality and the residual plots. Before, this is a residual plot. You can see it's not looking good at all. And the residual plot, after we've been able to obtain the logarithmic transformation of the variables, you can see the residual plot does not show any pattern. Because there's no pattern, of course, that shows linearity as option hold. And as you can see, when you take a look at the variance of the residual given any value of the fitted, that is more or less like equal variance. Okay, so if you want to generate the plot, of course, you're going to do plot mode 2,1, just like what I said the other time. Now, investigating for normal QQ plot in normality now, basically going to use normal QQ plots. Okay, and of course, that is a coding out, if you basically want to do that. For the untransformed variable, you can see there's a violations of normality. But when we now transform the variable, of course, you can see that lines up. Okay, so which means the transformation and effort actually work. Okay, so why does the log transformation work for this study? Okay, why not the square root transformation, or why not other form of transformation? Okay, now when I say log transformation, I'm actually referring to natural log. Okay, so the reason why transformation, the log transformation work in this study is because initially the relationship between the variables is multiplicative in nature. I'm going to say that again. Initially, the relationship is multiplicative in nature between the brain weight and the body weight. It was actually non-linear. Okay, now which means the brain weight, okay, is basically going to be expressed as this, where I'm actually going to have a body weight raised to power beta 1. Okay, that was the origin. And during transformation, okay, we are taking the log of the conventional model. Okay, I take the log of this guy, the log of this guy. Of course, this guy is going to come down when I do that. And of course, I'm basically going to have this now. Take a look at that. Okay, when I'm taking the log, I'm going to be log of this guy, log of alpha. Okay, plus, multiplication is going to be a plus, and the multiplication is going to be a plus and log of that. So this beta 1 now is going to come down, right? So when the beta 1 come down, I'm actually going to have this. So which is what we fitted. Okay, so the origin of this guy is this guy. So which means initially, the relationship between the brain weight and the body weight is actually this. Okay, so transforming, which means it was a non-linear. Okay, so transforming the non-linear now with the introduction of log at both sides, and that was what led to this, that we successfully feeded. So when we feed this guy now, okay, it's actually a work. Okay, so which means when you see a log in a variable in a model, then it means uh that's a transformation that actually work. Okay, in order for the for us not to have a violations. Okay, that's what we mean. Okay, what if you don't know what the model is supposed to be like? Okay, this is what the model is supposed to be like. We did not even have that in mind. What we were doing was that, okay, we're just trying to investigate which transformation that are actually going to work. Okay, so in the future lectures, general process for variable transformation, I'm actually going to walk you through that. Of course, that is what we're going to do on Friday, where we're going to look at transformation, different kind of transformation we have around, using statistical software. Okay, so the takeaway from what we've done. Of course, the power transformation, if W is having issue, okay? The idea of the power transformation is basically going to work. Okay, the W raised to power lambda, if lambda is not zero, but the moment lambda equal to zero, it means we're doing a log transform. So which means in the problem that we just solved, okay, we actually believe that the two variables, both the response and the predator, we raise them to like the lambda was zero. Okay, when that was why we basically use the log. Okay, now I'm going to say the power transformation is very useful. Okay, and useful in doing what? Of course, it's very useful in making sure that that we don't have violations. Because if you have violations, it's a way to fix violations. And that was why and when I say violations, maybe it could be violation due to linearity or constant variance or normality or unusual observation. When you take a look at the example that I walked you through the other time, we only saw outlier, right? The African elephant. When we look at the weight of African elephant and the weight of Asian elephant, we realize that that was a we suspected outlier. And let me tell you this: outlier will induce skewness. When there's an outlier, it will induce skewness. So induced skewness, it means if your data is skewed now, it means your data is likely going to deviate from normality. Okay. And of course, linearity assumption may not also hold. So the power transformation is now very useful in obtaining linearity. Okay. Then it's used to stabilize unequal variance, obtain normality, as you can see, in the last example. And it can also be used to get rid of unusual observations. Okay, but let me tell you, that does not guarantee to fix the problems. I'm going to tell you why in our subsequent lecture. Okay, also, what if your variables values are negative? Okay, what if in a situation where you got your variable values are negative? Okay, so what are we going to do? Okay, the idea or, some other ideas is going to work. Okay, now I'm going to walk you through other form of transformation that we can actually have around. Okay, like a box course. Okay, give me 1 second. Okay, so like a box course transformation. Now, the box course transformation is another idea, that actually work. Okay, so I want to show you the box course transformation now. Okay, so a box cut transformation is actually a kind of transformation that we use to transform variable that doesn't follow normal distribution. And let me tell you this: if the distribution of data is not normal, what we normally want to fix is the response variable. Why do we need to fix the response variable? Because the distribution of the response variable is assumed to be the distribution of residual. I'm going to say that again. The distribution of the response variable is assumed to be the distribution of the error. And they need to have the same distribution if you look at what we've done before. And that is the reason why if there's a violation due to normality, okay, the variable that we normally want to transform is the response. So if we want to transform the response now using the idea of box cost, okay, we want to use a box cost transformation now, right? Now, the original value is basically going to be y. The new value is going to be y raised to power lambda minus 1 divided by lambda for y, for y not, equal to 0. Okay. Now, I think I wanted to say for lambda not equal to 0. So, yeah, y not equal to 0, yeah, and lambda not equal to 0. So here, when lambda equal to 0, we're basically going to use log y. Okay, now I'm going to walk you through this guy now. We got two variables, x and y. We are actually we're looking at the relationship between x and y. Okay, take a look at that. Maybe we realize there's a kind of violations or normality, and we basically want to use the idea of bus course. Okay, so this is going to be the code. This particular code now, we actually generate what is the value of lambda that work. Okay, the optimal values of lambda that actually work. So it's basically a negative 0.424 now. So if I want to run a new model, okay, the response variable that I'm actually going to use in the new model, don't forget, the transform one I said is going to be y raised to power lambda minus 1 divided by lambda. Okay, now, so that's what I'm programming now. That's what I'm being, I'm programming here now. Okay, I already know what my lambda is. Okay, so I'm basically going to plug in. This is my new variable now, the transform response, putting into consideration the lambda to be negative 0.42424. Okay, that is the new variable that I'm actually going to run. Okay, now how do I know the new variable, the transform variable work? So I'm just going to revisit, investigating for normality. Okay, by trying to get the QQ norm, okay, of the when you say the QQ norm of the original model, there's going to be violation, okay, and by the time you now transform and you do the QQ norm of a new model, let's see what happened. This is a QQ norm, okay. When you take a look at the first one, okay, it's basically the old model. You can say violation of normality. For the new model, we have already fixed the problem now. Now you now see the idea of bus course actually work. So the bus course is targeting, addressing the normality, the normality. And when I talk about the normality of what, we're going to be focusing on the response variable, which is the outcome variable, which is also what we call dependent variable. That was the one that we transform, okay, using the idea of bus course, okay. Oh my God. So that is going to be the end of the lecture. So in this lecture, of course, I actually walk you through the transformation effort that work. The takeaway from what I've presented today is that when there's a problem, okay, when you are trying to investigate relationship, okay, like I said, we got 4-step process. The number one in the 4-step process is basically you're going to specify your model. You specify the functional form of your model. And I know you're basically going to specify the functional form of your model using the principle of subjectivism. Okay. Now, the number two now is you basically want to like estimate your model estimation. So which means you want to estimate the parameters in your model. And after estimating parameter in your model, we don't just take a decision. So what we're basically going to do, in order not to mislead, we basically going to, we're going to conduct a test on our model. We actually want to see whether the model is going to do a great job. And doing that, we need to investigate assumptions. Okay. So if you are trying to validate your model, okay, the only way you can do that is to investigate whether assumptions hold. When assumptions hold, you can trust your model. But when assumptions are violated, you cannot trust that model. Then you need the idea of transformation. And when I talk about these assumptions, we got assumptions of linearity, we got assumptions of constant variance, we got assumptions of normality, we got assumptions of independence, we get assumptions of, the absence of unusual observation that could be outlier or high leverage. Of course, the outlier, according to Benkamp in 1982, when you have a data point that is not consistent with the rest. Okay, and the moment if there's no violation, okay, then it means you can now use your model, like to answer the question, that make you to like, fit in the model in the first place. You can make inference, you can take conclusion. But what if in a situation where there's a violations, of course, we need a transformation. We need to transform the model. Okay. So that was what I actually walk you through, the different transformational efforts that work. Of course, I remember I started by trying, I use an example of, we're looking at the relationship between brain weight of elephants and the body weight. Okay. And in a way, we identify two outliers. One of the outlier is African elephants. The other outlier is Asian elephants. Okay, their values are not consistent with the rest. And according to Benkamp in 1982, they could be damaging to the model. And what we need to do is that we actually need to put the model in a proper statistical form. And that was the reason why we're now trying to exploit the kind of transformation that work. We try log, we try cube roots, we try square roots. We take the square root of both variables, we do the reciprocal of both variables. If you take a look at that very effort, it's like we're looking for a way to compress the data, because the African elephant and the Asian elephant will basically make the distribution of the data to be skewed to the right. Therefore, we needed an effort, to make it to come to the center. And the transformational effort that will work in that regard is basically to look at the one that can actually compress. That was why we're trying the log, the square root transformation, and the like. Okay. And I said that if there's a violation due to normality, now let me tell you this: if the presence of outlier could lead to other problem. If you take a look at the African elephant example, where we are trying to make a prediction of the brain weight of elephant from the body weight. Okay, we identify two elephants that are outlined, looking at the scatter plot that we generated. Okay, so, and do you know that that violation will automatically lead to other violations, like the presence of outlier will lead to violation of normality, of linearity, and so on, like that. Okay, so, and that was why we investigated using the residual plot and the QQ plot. And as you can see, those assumptions were violated. And by the time we fix that and we reconstructed, we actually performed the test again. I mean, we generated a diagnostic plot again. I mean, the normal QQ plot and the residual plot. We saw that we were able to fix the problem. And when there's a violation due to normality, maybe there's a violations of normality assumption. And I said, in order to fix that, we normally address the response variable, the outcome variable. Why? Because the response variable, the dependent variable, is actually the one that is subject to variation. And it is assumed that this probability distribution of the response variable is basically the probability distribution of the error. And that is why we fix the problem, trying to transform the response variable. using the box cost transformation. Okay, so on Friday, I'm actually going to explain further example on transformation techniques. Okay, so be sure you stay safe and have a lovely day. So bye for now, everyone.